There's been a lot of attention on Francois Chollet's ARC challenge recently. Now, the ARC challenge is around 1,000 different challenges that are based in a 2D grid world, and they resemble intelligence tests, which is to say you just have a few examples, and the goal is to extrapolate or to generalize from those few examples. The reason why Chollet invented this back in about 2017 was his genius recognition that there is a knowledge gap in deep learning models. Deep learning models are a little bit like an interpolative database, which means they generalize really well when they've seen lots of data about a particular problem. But when there is an explicit knowledge gap, you need to do reasoning, because reasoning is knowledge acquisition. So if the knowledge is not in the language model, then the language model isn't going to help you very much.
If you could collaborate with any AI researcher, who would it be and why?
Chollet. That's an easy one.
Love Chollet.
Love to hire him. If you're for hire, email me and I can't pay nearly as much there.
I'm really worried I pissed Chollet off. I hope I haven't, because I love him. He's still my favourite person. But we did a thing on the Chinese room, and I got him to record like a little 15-minute spiel about it, and he was coming at it from the whole functionalism thing, you know, that like it kind of emerges, consciousness emerges when you have functional dynamics. And I said, I'm going to give Chollet the benefit of the doubt, and I should have edited that out because it sounded like I was like mansplaining to Chollet, which wasn't my intention.
That's probably
like,
fine.
About 10 people messaged me like in quotes, I'm going to give Chollet the benefit of the doubt.
Oh shit, okay.
I
wouldn't have read it that way, but
I shouldn't have done that. Yeah, I love Chollet. You know I love Chollet.
Certainly.
Yeah. Anyway, so who would it be?
I have no idea. Like, I don't know. In terms of working, I don't know what anyone is like working together, right?
Would you work with LeCun?
Sure.
Yeah.
Why
What
not?
would you work on in?
I don't
What
know.
would you
Whatever
work
they
on
want.
with
He probably has a team that does stuff. So
Yeah.
I'm not
Okay.
too set on particular directions.
Okay.
So the ARC tasks were discrete, they are combinatorial, and they're designed to be minimally interpolative. Now, personally, I think that they can still be interpolative. I mean, language is discrete. For me, it's more about the fact that they are low-frequency data, so they haven't been sampled during training, which is why the assumption with a measure of intelligence is if you can broadly expand your horizon from a few examples, normalized by the amount of priors and experience you have, then it's intelligence. So Francois Chollet's measure of intelligence is technically non-computable. If you look at we won't talk about the formulas now. By the way, we're interviewing Chollet very soon, so we'll kind of save the foreplay for that episode, and we'll talk all about the measure of intelligence again and the ARC challenge in more detail. But the basic formalism is non-computable. Okay, and what it intends to measure is generalization efficiency, right, or knowledge acquisition efficiency. Something like ARC serves as a good proxy for intelligence, because if we assume that there was a knowledge gap and we have an algorithm which fills in the knowledge gap, and we can make certain assumptions that the algorithm isn't cheating because it hasn't seen the private set, so nothing's leaking from the private set, and the algorithm isn't taking statistical or perceptual shortcuts, then we might make the assumption that the algorithm is intelligent. Now, ARC is a really difficult problem because we only have a handful of examples per challenge. If you think about it, there are something like 10, which is the number of colors to the power of 900 possible combinations for a given challenge. So this is an absolutely huge search space that we are traversing through. Out of all of those possible answers, exactly one gives you the credit, which means it's a very sparse problem. So there's a really cool paper that introduces ARC, actually. It's called Neural Networks for Abstraction and Reasoning Towards Broad Generalization in Machines, and it's by Michael Hodel. And it talks about these Bongard problems, which were originally conceived in 1967. And humans can look at these things and they can recognize analogies. So we have some kind of perceptual inference, and then we kind of transform a problem into system 2, which is the space of analogies. So this is really interesting, right? So it's saying, can you identify the difference between the two sets where each problem encapsulates a different concept? So if you look at the concepts here on the left and the right hand side of the vertical line, you can see that the first one is playing on the concept of connectedness. So the 6 figures on the left-hand side are line drawings which are not connected together. And on the right-hand side, there's a gap, so they are disconnected. So we look at that and we say, that's connectedness. And on the far right-hand side, this is the concept of inside. So the little square is inside the containing structure on the right hand side, and on the outside, on the left side, it's outside the containing structure. So we recognize this as an inside of abstract concept. Now for me, the ARC challenge is all about efficiency, right? So what we need to do essentially is search a massive space of possibilities, but use intuition like we do. Because when we look at an intelligence test, we very quickly hone in on the nub of the problem. We use these mental heuristics. So we're doing the equivalent of searching this huge combinatorial space where we compose together all of these different skill programs in a creative way, and we very quickly happen upon the answer. That is what intelligence is. So brute force searching all of the possible combinations of these skill programs that we have, it's not intelligent. So a huge thing with the ARC challenge is to have some notion of this huge library of sub-programs and search the space of combinations as efficiently as possible. Now, an abstraction can be thought of as a commonly reoccurring sub-program. So the thing that we seem to do is we start from this kind of basis set of fundamental sub-programs, we compose them together, and when patterns or sets of compositions work really well, we seem to kind of consolidate that into a single program, and that gets embedded into our library. And over time, our knowledge grows in that way. So you can see here, there are some examples here of typical ARC challenges. It's a 2D grid world where you have, I think, 9 possible colors. Now, all of the ARC problems work on the basis of core knowledge. So this is a really popular idea in psychology, that the way we think about things is we have this core knowledge, and the way we do reasoning is by recombining that core knowledge into a new situation. So it's almost like conjecturing in mathematics, where we have all of these deductive rules about how the world works, and that's like a generative model. So we can produce this huge tree of combinations of those rules, but we have this creative ability to heuristically combine them together in an interesting way. So the core knowledge that is used to generate the ARC challenge are objectness priors. So this is handling objects and their interactions. Goal-directedness prior. So many of the tasks involve a general notion of intentionality, finding the simplest solution to some problem. So for example, drawing the shortest path through a maze rather than a longer one. And here are some examples of ARC challenges. So in the top one, you can see that we have some kind of object, and where there is a hole in the middle, which is inscribed by green squares, it's quite obvious looking at this that the goal is to insert a yellow square where there are green squares surrounding it up and down. So you can see there's 1, 2, 3, 4, 5 examples here. And then we've got the question mark, which is the test instance. So clearly what we would do here is fill in a yellow dot in all of the situations where there are black cells inscribed by green cells. Let's look at the next one. By the way, what you should notice here, by the way, is that the size of the grid of the input and the output can be different. Because on this one, we have an 8x8 on the input and we have a 4x4 on the output. So this next one is very challenging. So you do need to be quite smart to do these things. So the next one is transforming it into a 4x4 from an 8x8, and we are superposing the quadrants on top of each other in a certain order. And you can see here that it's happening in a clockwise fashion starting from yellow. So the top right quadrant always wins, which is why the top right quadrant is perfectly expressed in the test example. So this is a pretty difficult one. The next one, let's look at this. So I'm actually looking at this for the first time. So in the next one, when we have a red dot, we inscribe it in the 4 diagonal corners with yellows. When we have blue, we inscribe it vertically with orange. And we can see on the third instance that when we have a pink one, we don't inscribe. So on the test instance, we would inscribe the red and the blue but not the cyan or the pink. The next example here is quite straightforward. So we have a mosaic pattern, and this is a denoising prior. So whenever we have black, kind of like missing cells, we inscribe the pattern of the mosaic into those black cells. So that one's quite simple. Now this is pretty cool. So this talks about the first winner to the original ARC challenge, which was hosted on Kaggle in 2019, and it was by this guy Johann Socrates Wind, and he implemented a domain-specific language, so a DSL, with 142 handcrafted unary functions on grids, and these are functions which perform various different transformations that represent all of these things that we we're just talking about. So things like, symmetry and movement and denoising and so on. And what he did was, from a particular instance, he constructed a DAG, so a directed acyclic graph. Basically think of it as a tree, and he greedily sampled all of the different transformations, I think doing a breadth first search. And then he had to have an evaluation function. So for every sampled trajectory on this DAG, let's look at the Hamming distance or something to see how close is it to the test instance. And then he presumably selected, let's say, the top whatever sets of transformations, and then that became the program used for the final prediction. So I think that did around 20% on the hidden test set, does it say? Something like that anyway. It also goes on to talk about a neurosymbolic approach with Dreamcoder. So Dreamcoder has a waking phase where it generates programs to solve tasks, and then it has oh, by the way, an interesting thing here is that Dreamcoder is bootstrapped with a domain-specific language known as a library, and the library contains a set of functions and values defined with a functional type system. This is really important, right? So when you generate just syntax, which is code, the space of valid syntax is much larger than the space of valid typed syntax. So having some kind of a compiler or a type checker allows you to dramatically cut down the space of possible programs that you generate. So you can see there are some examples here that there are types of integer and string and various different discrete sets of values and different function mappings. And in this particular case, the waking phase would generate programs that are constrained with this minimum description length. So this is very similar to Occam's razor, that we should find programs that are as simple as possible, because in the natural world, simple things seem to generalize and work much better than complex things. So yeah, Dreamcoder then had this abstraction sleep, which was essentially you look at recurring motifs in the generated programs, and then those become kind of condensed into primitive functions that can then be composed out of the DSL in the waking phase for producing new programs. So this is something very similar to what we do. When we sleep, we consolidate our knowledge, and then that makes us better at reasoning the next day. There's also a dreaming sleep, which is where the generative program is guided by a neural network, and we fine-tune that neural network, which means when we generate new trajectories on that neural network in the waking phase, it's kind of guided by what was previously successful before. So we're kind of iterating through this waking phase and these two sleeping phases to produce this neural guided program search. And Dreamcoder is a really, really cool idea. It was by Kevin Ellis out of Josh Tannenbaum's team at MIT, and we've never done an episode on that, but maybe we should, because I think it's a really, really interesting approach for program synthesis. So what does a good solution to the ARC challenge look like? Well, to me, it's all about the efficiency of reasoning, which is like at the time when we have a test instance, we need to search this big space and we have to do it as efficiently as possible. So the original winner back in 2019 was just basically a Python program, just searching this space of combinations of all of these knowledge priors, selecting one that worked well based on an evaluation function. So that's the first thing. But what about using language models? Well, you can just get GPT-4 to generate a Python program or some kind of intermediate DSL, which is what the Dreamcoder thing did. And when you use GPT-4 to generate the Python code directly, you get around 10%. That was the previous state of the art. what the guys did that we're talking with today, so Jack Cole's team, which was the previous winning solution with 34%, they fine-tuned a language model. So before you do anything, fine-tune it on dataset augmentation on arc tasks. So that has the, the behavior of kind of like moving archetype problems into the language domain if you encode it in a certain way, and then doing test time augmentation or active inference. So when you have a test instance, you then do a bunch of augmentation around that, you fine-tune the language model again, and then you get the language model to generate the program. So they got about 34% with that. It's worth noting as well that they were limited in compute and they were using an older language model, which was unimodal. So it's entirely possible that their results will continue to improve in the future. So this guy at Redwood Research, Ryan Greenblatt, he has put a Substack article out claiming to get 50% on the hidden test set on Arc. And he said that he has achieved this in 6 days. So he said, I recently got 50% accuracy on the public test set for Arc AGI by having GPT-4o generate a huge number of Python implementations of the transformation rule, which is around 8,000 per problem. So, essentially the idea is we have the base GPT-4o, we send the image up of the problem, although he did say that the vision model wasn't particularly good, although it is interesting to have a multimodal variant. He used a grid ASCII2 encoding to represent the Arc problem itself. He did a bunch of prompt engineering, but of course you can't fine-tune GPT-4o. So the interesting thing about his solution is that there's actually surprisingly little domain-specific tuning other than prompt engineering. He did say that he did some feature extraction on the Arc problems, which is to say finding connected regions and describing in text how those connected regions were related to each other. But it's certainly much more broad than the other solutions that I've seen so far, which are very psychology-orientated and very hand design-orientated. He said that he uses few-shot prompts, which perform meticulous step-by-step reasoning. He's used GPT-4o to try and revise some of the implementations after seeing what they actually output on the provided examples. He did some feature engineering, providing the models with considerably better grid representations than the naive approach of just providing images. Now, what's interesting about this is it's a neurosymbolic approach. So it's not just using language models, it's using the language model to generate a whole bunch of candidate programs. So yeah, he said his approach is similar to AlphaCode, which a model generates millions of completions attempting to solve a programming problem and then aggregates over them to determine what to submit. He said he's getting a 50% with this main idea, took him 6 days of work. So he said that the high-level method he used is provide the Arc AGI problem to GPT-4o with an image representation with various text representations for each grid in the problem. The text representations showing which cells are occupied by different connected components of colors and showing diffs between the inputs and the output in cases where the grid shapes are the same, and instruct GPT-4o to reason about what the transformation is, reason about how to implement the transformation as code, and then finally implement the transformation in code. He said he uses a few shot prompts with carefully selected handwritten examples of step-by-step reasoning to actually get GPT-4o to do this reasoning somewhat effectively. The resulting prompt is usually around 30k tokens, including images. He then says out of those 8,000 completions, take the 12 most promising ones and then try to fix each by showing GPT-4o what this program actually outputs on the examples, and then getting GPT-4o to revise the code to make it correct. And he does 3,000 completions that attempt to fix per problem. So he's doing 8,000 completions originally, and then 12 times 3,000 completions on the most promising candidates. He says then, finally, they select 3 submissions to make, which is based on a majority vote over programs which get the examples correct. So then he says, what are the returns to more sampling? And this is quite interesting. So the more samples that you take in terms of the original completions and the refinements, there seems to be a scaling law where the top 3 accuracy just goes up and up and up. Yeah, so here he's got a graph showing his scaling law, and he's essentially saying what is the relationship between the top 3 accuracy and the number of completions. It's not entirely clear to me how he's done this. I think he's kind of added up the completions for refinement and the original generation, but I guess it doesn't make a huge difference. And then he's got some fit lines where he extrapolates that scaling outwards, and based on that extrapolation, he's kind of saying that it would get up to 70% performance, which is roughly human level, when he would take 2 to the power of 21 samples, so around 2 million programs, which is kind of interesting. And as you can see, the accuracy is significantly higher when you do refinements. So when you do refinements, you're getting significantly more accuracy, even with significantly fewer completions. He said that the vision model was terrible on grids. It often fails to see the input correctly and states wrong facts around what colors are in some location and what shapes are present. He goes on to say later that he thinks that this might be a significant improvement in this approach when the multimodal vision models actually have better visual recognition. So he's kind of saying here that the multimodal aspect isn't actually a big determining factor of why this works. He said that GPT-4o is not good at coding, especially not for the sort of geometric manipulation problems that we're talking about here. And he also said that they don't do multi-round debugging because it's probably cheaper and more effective just to do more samples than the current regime. He also says that GPT-4 is worse using long contexts and that it kind of degrades significantly after 32K. And this also affects the kind of the utility and generalization of this method, because when you have problems that can't be encapsulated in a 32K context, then presumably it wouldn't work very well. He was quite generous in saying that he used about 1,000 times more runtime compute per problem than prior work on this benchmark. So maybe Jack Cole's approach could have scaled better if he had access to this amount of compute. He also said that the submission is ineligible for the ArcAGI prize and the main leaderboard, as it uses a closed source model and too much runtime compute. And I think, in principle, it does go against the spirit of the Arc challenge, because, all he's done is kind of like used the memorization power of the underlying language model to generate a whole bunch of programs, and then done a brute force search with an evaluation function over the generated programs. So you could argue that it's not really reasoning efficiency in the spirit of Chollet's metric. So he goes on to predict that he thinks there's a 70% probability that a team of top 3 research ML engineers with fine-tuning access to GPT-4o and a year of time could use that model to surpass, typical human performance on ArcAGI. He also reckons that human performance is actually around 70%, not 85%. Another big thing that he talks about is this definition of in-context learning. So Chollet, of course, says there is no in-context learning. Language models are databases, and what you're doing is you're retrieving a program based on the prompt. And Brett is making an argument here that these things are doing in-context learning. So Chollet said that if you were right that LLMs can do in-context learning, LLMs would do really well on ARC puzzles, because ARC puzzles are not complex. Each one requires very little knowledge. Each one of them is very low on the complexity scale. You don't even need to think very hard about it. They're extremely obvious for humans. Even children can do them, but LLMs cannot. Even LLMs that have 100,000 times more knowledge than you can still not. The only thing that makes ARC special is that it was designed with this intent to resist memorization. That's the thing, like ARC challenges are designed to be representations of problems which the language model does not know about. So they are an exemplar of this knowledge gap. Yeah, so he said that based on his results, you have to reject one of the following claims. The first one is getting modest performance on ArcAGI, so let's say 50% plus, requires at least a little bit of runtime learning on each problem. The second one, program selection on only a moderate, so let's say 6,000 number of programs, like the way he does it, doesn't count as learning in the typical way people think of learning. Or finally, current LLMs never learn at runtime, which is to say the in-context learning they can do isn't real learning. So he concludes that claim 3 is false. He thinks that LLMs can do some relevant learning when doing in-context learning, even though overall performance is incredibly weak, which is to say he has to draw 8,000 completions of programs, but he still thinks there is some learning nonetheless. Anyway, let's not forget that the whole reason Chollet invented the ARC challenge was that he was exasperated that many solutions to Kaggle challenges were so overfit to the particular instance of the problem that they would not generalize to other instances of similar problems. Now, that doesn't really seem to be the case with these ARC, recent winners, and even with Ryan's solution. I can see how, even though they require a prodigious amount of computation, they could be used for other similar classes of problem on other similar types of geometry and domain. But they are certainly task specific. You know, the whole point of the measure of intelligence is developer aware generalization, which is that the algorithm, you know, the meta learning system or the intelligence system can generalize to problems which the developer of the system was unaware of. This is still, in my opinion, somewhere between a specific problem and a domain or a collection of problems. So I do think that this approach could be used for solving, you know, fairly similar domains of similar problems, but it's definitely quite domain specific, I would say. Okay, so to sum up, solutions to the ARC challenge: doing some kind of, you know, let's say a Python program which does test time augmentation using the application of domain specific priors to, you know, and an evaluation function to find out some kind of reasoning pathway of transformations of the problem to produce the answer. So that's this kind of program search type thing. And there's a neural guided version of that, which is Dreamcoder, which is when you use a neural network model to guide the generation of programs. And the generation of programs can also be a neural network, or it could be a DSL. So that's very interesting. There's just a plain program generation with language models solution, or there's something like what Ryan has done here, which is generating many completions and then evaluating those, you know, using a Hamming distance, and then refining those, you know, like let's say the top 10 ones of those with you know, with a language model, and then picking the top 3. There are some interesting solutions from Jack Cole and his team, and they're going to be on the show later. Another thing that we will talk about in the conversation later today is language models. They have a certain type of prior, an inductive prior, because if you think about reasoning, you have to think about where does the reasoning happen, because the reasoning always happens somewhere. So the reasoning could happen in the you know, in the data generating process. So in a way, we're doing reasoning as a collective intelligence, right? We're a whole bunch of humans, and we're trying many different combinations of things, and we're evaluating them, and we're rinsing and repeating, and the things that work stick. They get embedded in our culture as kind of social programs in our language, and then we use them again. So we're doing reasoning in our native data generation process. When we do data generation algorithms for machine learning models, that's also a form of reasoning, right? So, you know, essentially we're augmenting many different types of combinations of things. We're producing a data set, and then we're memorizing them in a language model. The inductive priors themselves in a language model are a form of implicit reasoning. So in a self-attention transformer, it does this permutation symmetry transformation, right? And essentially what it's doing is it's permuting, it's generating many symmetry transformations of your data, and it's embedding it into the neural network. So that's a form of reasoning. Another form of reasoning is inference time reasoning, where you have a base model and then you traverse it in many different ways with an evaluation function, and you can do reasoning there. You see where I'm going with this? There's many places in the predictive architecture where you can do reasoning, and all of these different approaches to ARC kind of play with doing reasoning at different points in that process. Now, one of the things I'm interested in seeing is, you know, self-attention transformers. They've got this permutation symmetry, right? Works really well, works well in many situations, but what's really difficult to do in a neural network is to mix different types of symmetry transformation in a single model. And this is what the GDL, you know, the Geometric Deep Learning Blueprint, is all about. So it would be interesting to have a hybrid approach where you actually have different symmetries, you know, so different models with different inductive priors that represent different symmetries, and you use those symmetries in some kind of an ensemble or combination to guide the program search. I think we've not seen that yet. Most of the approaches I've seen so far just use a single model which respects a certain type of symmetry transformation. And I think another big thing that we're going to see in the future is multimodal models. So Ryan said in his Substack article that the vision capabilities on GPT-4o suck, and I can imagine a future where multimodal models with, you know, very good visual comprehension actually improve the situation much more. So I think that'll be a big source of improvement going forwards. But it's quite interesting right now that we have reasoning which is diffused at many different steps of the predictive architecture. And as the models become better and more general, then they'll do more implicit reasoning, because the models, they are basically databases, they're interpolative databases. But the more that they do implicit reasoning, right, then the more reasoning we need to do pre and post hoc, which means that the model itself is more intelligent. And that's something that's really exciting, because right now we have to generate thousands of completions and we have to refine them and we have to evaluate them, and all of the reasoning is post hoc. But as the models get better and better over time, the post hoc reasoning can be, compacted, because the models themselves will do more implicit reasoning. Now, I think it'll take a very long time for that to happen. And another thing is, reasoning is just difficult. Machine learning models, they have a finite capacity, and that means there is a limit to the depth of reasoning that they can memorize, because the models themselves, they're not doing reasoning on the fly, they're just memorizing reasoning, because all of the reasoning in a model was implicit reasoning, which was embedded into their weight during training. The models don't do any reasoning at inference time. It's a database lookup, right? So that means because the models have a finite capacity, they are finite state automators, there is a limit to the complexity of the reasoning pathways that can be crystallized into the model. And that's why I'm a fan of active inference, because I think the real world is more complex than anything that we could ever memorize in a crystallized model. Every single situation has novelty and complexity. So the way we deal with that is by having a predictive architecture that actually leans into novel complexity by doing active inference. And what that simply means is, I'm in a novel situation and I have to figure out what works in this situation, but I can still use my base knowledge in my language model. I can do some reasoning by searching through a whole bunch of primitives, and then I can bake those into the model, which means when I'm in an analogous situation in the future, I don't need to perform that reasoning because it's crystallized in the model. So this process of doing reasoning in the moment, baking it into my model, for me, that's how we do it, and I think that's how we should build our predictive architectures. So yesterday evening, I was interviewing, at the time, the worldwide winners of the ARC Challenge with their 34% entry on the private set. As of this announcement this morning, by Redwood Research, I guess they've technically lost their number one spot. But anyway, so it's Jack Cole, Michael Hodel, and Mohammed Osman Abdelghani. So Jack Cole has a company called Mindware Consulting Incorporated, and he's also created a few successful apps that he says has over 30 million downloads. He has a PhD in clinical psychology, and he maintains a part-time psychotherapy practice. He says he's got a background in cognitive testing and neuropsychology. And he was inspired by Yannick Kilcher's original exposition of the ARC Challenge, and I think he hangs out a lot in Yannick Kilcher's Discord. So also joining us this evening is Michael Hodel, who's worked very closely with Jack Cole and Mohammed, and he's got a paper out called Addressing the Abstraction and Reasoning Corpus via Procedural Example Generation. So this dataset generation is really, really important. The entire team used this in order to fine-tune the language models, both at pre-training and at inference time. So in this paper, Michael talks about this task generalization, so essentially a procedural algorithm that uses all of this core knowledge to, extend the ARC data set, because it's really important in deep learning models to have a lot of data, to have data density, because otherwise it's just sparse and the model won't actually learn generalizable patterns from that thing. So one of their approaches was to generate a much larger ARC data set, fine-tune the base model on it, as well as doing test time augmentation. And it was Michael's work in particular that the team used in order to get their winning solution. So Michael will be joining us today. Also joining us today is Mohammed Osman Abdelghani, and he is a senior AI researcher with 4 years of work experience developing deep learning models. He has multiple successful real-world machine learning deployments under his belt, using transformers to tackle challenging problems in computer vision, reasoning, and natural language processing. Now, he's a really, really smart guy. I was very impressed with Mohammed, and he's looking for a PhD position at the moment. So if there are any university professors watching this who wants to have a very smart, motivated guy do a PhD under your wing, please reach out to Mohammed, and his email address is in the video description. Yeah, Mohammed said that him and Jack are hugely, kind of informed by this psychology approach, which is really interesting. So that means core knowledge and, handcrafted cognitive architecture design. Like the psychology approach to AI is basically based on this idea that we have a base set of fundamental reasoning primitives, and we kind of compose those together as part of our reasoning process. And that is the core of symbolic and neurosymbolic AI is this idea that we compose core knowledge into novel programs to suit the situation. So anyway, I had a really good conversation with Jack, Mohammed, and Michael. We spoke about their submission, what their thought process was. I clearly challenged them a little bit on whether it is in the spirit of the measure of intelligence, because I think of all of these solutions to the ARC challenge as being very inefficient, frankly. But they gave me quite a bit of pushback, and actually they gave me a lot to think about. I definitely updated quite a bit based on this conversation. I'm going to be filming with Chollet very, very soon. That will be a special edition. So we're planning to release that show in August. So this is a very interesting development, actually. I'm glad that all of this has happened. If you have any questions that you would like me to put to Chollet based on these recent developments, let me know in the comments, and I will be sure to ask Chollet all of your best questions. The other thing is, you should think of this as an office hours show. So I'm not, our production cycle on MLST is running into the months now. It's getting very, very difficult just to get anything out there. So this is just a very quick, just think of it as a fairly off the cuff conversation, because given the timely nature of this, I think it would be better just to get it out as quickly as possible. So, take that hedging as you wish and enjoy the conversation. I don't know where we should start with this. Who would like to describe in broad terms what the ARC challenge is and what Chollet's measure of intelligence is?
I think in broad terms, what the ARC challenge is a benchmark for, I guess you could say, artificial intelligence systems. I don't know. It's not really for machine learning per se, but it's just a benchmark to try to provide a really strong challenge that kind of goes beyond what you would see with the typical benchmark, in that he tried to make it where it's not gameable, meaning that you can't just memorize a bunch of facts or things like that and perform very well on the challenge. And so essentially that comes down to looking at it as a kind of like a measure of intelligence. And so I don't think he intended for it to be like a perfect measure, and he knew from the beginning that it wasn't like an ideal measure, but it's a good kind of starting place. And I think he's trying to get people to focus on meta learning in a sense. So basically he wants people to be able to develop solutions that can learn from a few examples and be able to generalize from those few examples.
And just to add to that a little bit, there exists other meta learning data sets, right? And kind of just a couple of interesting things is there's been papers that show that actually on these even vision-based meta-learning papers, you find, you try to have model, you look at the models that do really well, and you look at the meta-learning methods, and you find that they're actually shortcutting, right? They're zero-shot methods. So there's a distinction that you have to make between zero-shot models, right, where what they know is these shortcut kind of statistics, and they have really good knowledge about textures and objects and so on. Like, for example, it is kind of difficult to do to have a very good meta learning data set with something like vision. Like, even if you have held out classes, the classical few shot problem framing is you get 5 completely new classes at test time and you have to classify them, but you could still be a very good zero shot, you could still achieve very good performance as a zero shot model, right, by just having really good features. Now, the thing that makes ARC so special and so interesting that we've been working on it all of us for so long, is that it really has this focus on acquired knowledge in a way that's different to other meta learning datasets. And one aspect of that is the reduced number of priors, right? It's kind of, everything's kind of simplified in a nice way. Another aspect of that is the fact that it's a transformation that you have to learn. I think that's also really interesting. Rather than a classification, transformation is much more information dense. There are more things to keep track of, and having the instance, right, be a transformation is something, well, it's more complicated. There's more to learn. There's more to figure out, right? So it has a much higher focus on learning rather than pre-existing knowledge, and I think that's how it achieves it, by focusing on complex transformations, right?
Chollet was a genius. He knew back in 2017 that these models were essentially memorization machines, and reasoning is knowledge acquisition efficiency. So he reasoned that if they didn't already have the knowledge in the system, then they couldn't, given a couple of examples, learn that knowledge unless we threw lots of knowledge at the system, during inference time or whatever. And there's an interesting point you made about in-context learning as well. In language models, I think that's a bit of a misnomer, because if you think of language models as a database, it's more like in-context database query. But Arc is really interesting because it has, let's say, 800 tasks, and we know that those tasks are not in the database. Then it's got nothing to retrieve. So Chollet's genius was knowing that even in principle, this problem wouldn't work on a neural network. What do you think, Michael?
Well, I think that may be a bit preoccupied. I mean, it's kind of open to which degree you can, via however you want to call it, say interpolation or memorization, game this benchmark, right? So, and I think that's actually a nice thing about Arc. The hypothesis, like performing well on Arc implies something close to AGI or otherwise super useful, is falsifiable, right? So we can, or that's at least how I like to view it, we can see it as a means to an end, or not just as a means to an end actually, but as the end itself, or we just pretend as if it were, and then we try to maximize that score, and then hopefully we learn a lot from that endeavor. Yeah. So I mean, I think I wouldn't agree with the take that in principle you can't learn to perform well on Arc-like tasks. Yeah.
Oh, I mean something like a deep learning model. So just to comment on what you said before, so I agree it's a proxy for intelligence. Chollet's measure of intelligence is not computable. So we have something like Arc, and we make the assumption that if we can solve something like Arc, which is to say if we can reason, which means if we can basically construct, acquire knowledge efficiently on the fly to fill in a skill gap and do the thing, then we must be intelligent. But with the caveat that Arc is leaky. There's lots of perceptual shortcuts, as Mohammed was talking about. There are presumably lots of ways to cheat Arc. But the base assumption is a parsimonious good solution for Arc would be more intelligent-like.
If you look at like the viewpoint that LLMs are like just a database lookup table, like is that known for a fact, or is that basically an analogy? And so to my mind, if you integrate some other like recent research, if you look at like some of the interpretability work, maybe out of like Anthropic, and you see that these models are actually learning concepts and seem to be grouping things based on concepts. And if it is true that these models can learn concepts, then they can, then it may be that they can guide like the combination of the little programs that they learn based on concepts. And if you can do that, then essentially you have kind of a form of generalization. And so it, like these models kind of are prone to like shortcuts and memorization. And with our approach, we try to like basically not let the model do that. And so that's one reason basically that we use so many training examples. It's not to necessarily teach it so many concepts. It's to teach it a space around the concepts and to also prevent it from kind of using the shortcuts that the models are prone to.
A quick comment on that. I think, as an example, if you trained an LLM on chemical structures and then you did a t-SNE plot, it would reconstruct the periodic table. Especially if you trained the model on language of scientists talking about chemicals, because we have discovered the knowledge, socially, and then we've kind of embedded it in a certain way in our language and in the corpus, and then that'll be represented. But reasoning, to me, I think the interesting thing, I kind of agree that it's more than a database, because it's not a simulacrum. It is some kind of interpolative generalization around the corpus using this kind of vector space. And I saw that Anthropic paper, and it was very interesting. But, again, I think that the semantic categories are a reflection of ones that we've already found. But reasoning is really interesting because in ARC, it's about traversing this space of combinations. And given neural networks have a finite capacity, there is a limit to how many combinations they can memorize during training.
Just to add, I think there's an interesting dichotomy here that we can kind of establish and then move forward from that. And I think we can make some great points here. So can these models, just to speak a little bit more to what Jack is saying, can these models generalize? Well, we know they can, right? Starting from scratch in the training phase, right? They can classify the classes correctly and they're able to kind of form these concepts of classes and subconcepts and so on. And so we know they can do that. Now, at test time, what these models do, and I think this is something we can all agree on, this is a more common ground between us, is like at test time, they see a novel example, right? And they're able to, using the frame they've already obtained, they're able to kind of do a little bit more processing, right? But it's all within distribution, right? We're not talking about out of distribution. They can do a little bit more processing, right? And it's that type of processing that we're speaking to, right? So there is like when you see a completely new example of a mug and the background there is maybe like a different type of cup and you're trying to classify mugs and you have to kind of disambiguate. So there's a little bit of reasoning, there's a little bit of search, right, that happens there, right? There's no argument about that. And in the same way, when you look at an NLP model, right, given a brand new sentence, there is a little bit of figuring out what happens there. And I think the position me and Jack kind of taken and why we're teaming up, and we've been teaming up for so long. We were kind of talking about this from the beginning. Like System 1 and System 2, in our view, is kind of the same thing, right? It's just happening on a different scale. So we don't see actually a distinction between System 1 and System 2. That type of inner processing, and Michael also, I think, may agree with this, but yeah, that type of processing, I would say, is not so different from System 2 processing. Now it's time to kind of scale that up. And then there is, and so that's kind of what we were speaking to. It's not like LLMs are very good at generalizing out of distribution, or they are not going to memorize. They're going to memorize certain things, but you can kind of get them out of that. And if you look at the nature of the tasks that they were already able to do really, really well, right? And And if you kind of take this perspective, you can kind of see, okay, they're really good at perceptual tasks, and perceptual tasks are tasks that have you have to kind of deal with infinity. You have to wrangle an infinite ways of looking at the problem, and figure out a way of using first figure out the objective, right, and then implement that to find a solution. Now, there's another thing here that's really interesting. The process of going from scratch to generalization that I described in the training, that's also a very interesting process. It's a process where you were able to learn that frame and produce these generalized classes, right? The SGD or Adam or optimizer, right? Now, that's also another thing that should interest you when thinking about this. Okay, maybe you can incorporate that as well into the test time, such that you achieve more generalization.
Could we distinguish System 1 and System 2? 'Cause I kind of agree that, well, I think I agree. Let me just reason this out. I think a lot of people think the difference between System 1 and System 2 is discrete versus continuous. And Chollet, of course, made a distinction between those two because he designed the ARC challenge to show it as an example of System 2 generalization, which, presumably wouldn't work well with deep learning models. But to me, System 2 is more about it's more about the long tail. So it's about when you have discrete compositions of rules, you just get into this very sparse space, and that's the reason why it doesn't work on deep learning models. But just, maybe Jack, in your articulation, what is the difference between System 2 knowledge and System 1?
Yeah, I think maybe like one way you could think about it is, so like I don't know that you could make a great neuroscience argument for there actually being like a System 1 and a System 2, but I think it's a pretty good like analogy and something that is useful for understanding, the difference between like deliberate conscious reasoning in System 2 versus more perceptual, automatic, and non-conscious processing in System 1. And so I think kind of from our view, there might be like more of a continuum between these things rather than there being like some kind of a magical division or something between like the two kinds of systems. And so like one other thing that I think is maybe to bring in some concepts from psychology, and like one way I look at it is in terms of like the Cattell-Horn theory of intelligence, which is kind of a hierarchical way of looking at it, where you have like the G factor. And I think that's kind of backed up by a lot of research. But beneath that, you have fluid and crystallized intelligence. And I think Chollet viewed ARC as being a measure of fluid intelligence. And I think it seems like it's serving pretty well as that. Now, kind of to the point earlier of, are these LLMs like a database lookup table? So in some sense, I would say it like probably differently than that. I would say an LLM is a repository of crystallized intelligence. And to a point I think Mohammed made earlier is that the optimizer and the gradient descent process is the fluid intelligence of the model, or is a major component of it. So I think there's a little bit of fluid intelligence in these models that happens across the context when they're given an input. But primarily I think what you're accessing is the crystallized intelligence of the model. Now what we do in particular with our approach is we try to bring in more of the fluid intelligence aspects of it to be able to alter things at test time so that we get more of that effect. And some of the brittleness that is seen with LLMs is mitigated by the processes that we use.
Neural networks are a crystallized database, but it's a little bit more than that, because you have to ask the question, well, where does the fluidity come from in the generalization of a deep learning model? And in a transformer, for example, it's the inductive prior. So there's a kind of permutation expansion during training. So that's when, because at the end of the day, every neural network at the end of the day is an MLP. There is an MLP that represents any neural network. So the inductive prior photocopies different symmetry transformations of the input data all over this representation space. And then at inference time, we go and retrieve one of those representations. And you're saying, well, let's flip this thing on its head. And at inference time, let's do the fluidity. So that's when we actually combine different things together, and by the way, Chollet used the term active inference. I'm not a fan of this because I love active inference from the Carl Friston point of view, but it's still analogous in the sense that you're saying, I'm going to act, and then I'm going to, get some sensory information back, and then I'm going to update my model. And what this does, I think, is a form of lazy evaluation. So you're kind of lazily building the equivalent of 1,000 times bigger model, but because you're doing it efficiently by kind of, sampling information from the environment, it's computationally more efficient. But my test to you guys is that, isn't that against the spirit of the measure of intelligence, because you're still effectively building a big database?
Let's see. It's an empirical question. If the benchmark turns out to be gameable, such that you have something that scores really well, but you haven't gained any insight from that, so be it. That would be a shame, of course, but it would still be a valuable insight. So, I don't know. If you try to think of the space of all possible ARC tasks, it's extremely big and for sure extremely non-trivial to kind of write a generator that gives you like randomly samples from that space. So I think we'll just have to see how well it holds up. It's a very minimalistic framework, so these 10 symbols and at most 30 by 30 grids, but it obviously allows for an extremely great variety of possible tasks that you may encode in this ARC format. So I like to think of ARC not just as this specific set of 1,000 tasks, but really as a kind of style or format. So I would love to see if those specific 100 or 200 hidden test tasks seem to have been gamed or whatnot, to see ARC continue living and it being kind of an open or more open or dynamic benchmark. Yeah, but I guess we're still far from that.
I kind of have a question. You say, so how do you mean exactly game the system? Is it because we use the information acquisition, i.e. SGD, to create a database, in your words? Is that kind of the okay, I see. Yeah,
the augmentation, yeah.
The augmentation.
So by augmenting at inference time, we're just kind of filling in the database in the vicinity of where we need extra density.
Well, okay, yeah. Well, so it's kind of, ARC is a skill acquisition task, right? And kind of we really truly see the SGD as part of the model rather than something we're using to update the model. Like, this is the model. It's SGD plus the neural network, right? So I don't kind of see it as gaming if we're able to solve the task with the right. So if we're able to use
skill acquisition efficiency.
Yeah, exactly. In test time, right? So it's all within the ARC kind of framework that was laid out by Chollet. Yeah, I mean, the thing is, what's the best way to do that, and how to do that? I think we ought to have really like kind of no priors and preconceived notions of, okay, what makes what's the best way to do search, to do reasoning. Like, I think it's something a lot of people have a lot of different ideas about LLMs, but we try to come at it from a very blank slate. We really see, like I said, we agree about the system 1, system 2 thing. We've seen that skill acquisition, the best way to do that about perceptual tasks is to kind of learn, like we from the get-go we've been doing fine-tuning. Jack did fine-tuning over all the riddles, and his approach worked. I was trying a different type of fine-tuning from the start, right? Fine-tuning is a very common idea, but the reasoning behind that is because we believe, we agree with you 100% that reasoning is a search problem, right? I think that's what that's kind of one of the priors that people have, one of the preconceived notions. Okay, reasoning, there has to be search. We agree about that, but it's like, okay, what type of search and how wide, how many paths in parallel should you search for a perceptual problem, right? So if you see this as a perceptual problem with infinite possibilities and infinite ways of mapping input to output, okay, well then how do you search in the best way possible, right? And one thing I will say, just to give an example, is what object you look at in a riddle depends on the objective. So what object is relevant to you depends on your objective, and that's a key insight from psychology, right? The gorilla experiment kind of showed that. Like if I want to unlock my phone, then my unlock key is the object. But if I want to throw my phone at someone, then suddenly the whole phone is the object. And the same thing applies to ARC. You don't even know what object to begin searching from if you're not looking at everything at once and then finding out, okay, what's going on, what's the objective. So it's like, okay, you need to do a search, and reasoning is search, but this is how we're doing a search, and this is kind of the best, most effective way to do it, we think.
Yeah, I agree with you that reasoning is search, but I think there's more to it than that. So you're describing the kind of the frame problem, the relevancy problem in respect of some objective. And, when we look at IQ tests and riddles and so on, we have core knowledge, and you can get really good at riddles because you start to build a toolkit. You start to know that there are certain tricks, certain tools that you use. I was speaking with some guy who's an expert in mathematical optimization earlier, and he just said, oh yeah, after a while you just start to recognize this is a bin packing problem, this is a scheduling problem, and also you can recognize analogies. So you can say, well, this is actually analogous to this, and I already know how to solve that, so I can use this strategy in order to do that thing. And I've written down some examples here. Like the concept of connectedness, the concept of inside, the concept of monotonicity. These are all like, psychological priors that we have. And I think the spirit of the psychology approach and what Chollet was going for is that we do actually have this core knowledge, right? We have all of these base priors. Maybe they are natively imprinted. Maybe we learn some of them. And we do this search process, and over time, we build a library. So we start to kind of internalize and compact combinations of these programs into bigger programs. And then over time, we start to use the bigger programs heuristically. And we have this amazing ability just to look at a problem and to just very quickly compose together these skill templates that we have to construct a program that generalizes really well. It's really remarkable. Maybe Michael, you want to comment on that?
Yeah, it's a very interesting point. So I definitely think that this compositionality question is something that should be more heavily addressed by more people in general. And specifically in terms of ARC, what I basically did in the beginning, I followed exactly what Francois has suggested in his paper. Like I built out the DSL, and then I tried to use that, basically tried to search the space of all possible programs that I can write within this DSL. But I had kind of two realizations there. So one was a DSL, if you think of it as a toolbox or a set of functions which can rotate an object or mirror a grid or whatnot, they're really just that. So I would say what we bring as priors or knowledge, there's a lot more to just knowing individual transformations or such functions. There's a whole lot that was missing in my DSL relating to how do those components interact or how do you compose them together, all that sort of stuff. And eventually I just felt like, hey, come on, what I don't want to end up doing is have this handcrafted DSL and then write some search where I try to manually infuse some heuristics or hard code some rules on how to search. That's just like a static system that can't possibly be all that intelligent. So the kind of main realization that I had was, oh, I'm interested in machine learning. Can we try to view this as a learning problem? Obviously, all those core knowledge priors, or many of them, they occur elsewhere. They occur also in text, but they don't occur in this org format anywhere on the internet. So you can't directly learn from that and then transfer to the org domain. But obviously that's what Francois would love to see, right? Some system that has never been trained on org-like data and then still being able to perform well on org. But my thought was just mainly, we probably do want some kind of data generation process, which is also something that Francois has suggested in his paper, that's not static, but such that we can train within this domain.
That's actually a really interesting question that you just raised, which is, we're getting to the core of what does it mean in spirit to solve ARC. And I think the first level is the geometry of the domain. So it's a 2D grid world. And then there's the priors, which are things like rotations and reflections and, like things like agentness and so on. And I think personally, assuming that we are sort of nativists and we think there is core knowledge, I think the perfect solution would be in respect of a domain and the priors for that domain, it should generalize to any other sets of tasks on the same domain. Because I don't think Chollet actually cares that much about having a purely blank slate approach. Isn't that against the principle of psychology? Maybe Jack, you can talk to that.
Yeah, I think the whole blank slate idea is not really something that has been kind of borne out in terms of like research into human beings, and so I don't think we're not really a blank slate, and I don't think it's possible to have a blank slate system that has like no set of like knowledge where it can enter a domain and like just automatically understand what is happening there. And it has to be composable from the knowledge that you have. And so to my mind, like some of the symbolic approaches, I think they can do some deep generalization, but it's narrow. And I think a lot of ML systems can have a broader kind of generalization, but it's shallow. And what we try to do is try to deepen it some, like through the test time procedures.
Just to play back what you said that symbolic systems don't generalize very well. Machine learning systems do, but you also said the converse, that machine learning systems are narrow.
Oh.
So are you getting to the core of, in a continuous domain and on certain types of problems like recognizing cats, machine learning models generalize very well. But my intuition is that symbolic systems generalize in certain domains much better than machine learning systems because they are Turing machines. They can address a potentially infinite number of situations. They're completely different in principle.
Yeah, I basically kind of outlined two dimensions, and so I don't know if I'm completely right on this, but this is just kind of my intuition. So I see the symbolic systems as being able to do a deep generalization, but it's narrow. And so like Michael was saying earlier, when he developed a DSL for ARC. He eventually kind of realized that there was, well, when you hard code a system like that, it's only going to work in that narrow domain, but it might work in a very deep way. And so I see LLMs as having a wider kind of range of generalization, but it's more shallow. And what we try to do is we try to deepen it. And so like our particular model, and what I've tried to do is I've tried to go beyond ARC in the training to train it on like a wide variety of tasks. So if you take like a crafted DSL system for ARC, in no way could it ever generalize beyond that I can think of, unless like you actually design it very specifically to be able to do that kind of thing. And so I guess that's my point on it.
Yeah, maybe we should talk about your solution. So Jack and Mohammed, you worked on a solution, and Michael, you were the previous winner, if I understand. Maybe we should start with yours, Michael, and then we'll move into Mohammed and Jack. But let's sketch out what your approach was.
Sounds good. Yeah, basically, I set out to work on ARC, and first I built a DSL, which was an iterative process where, on the one hand, I added or modified DSL primitives, and on the other side, I used this DSL to construct solution programs for ARC tasks as a kind of in-development test of the DSL. So I do have reference solution programs for the training tasks. And then after that, I thought about, okay, now I have this DSL, how could I use it to try to reach some points on ARC? So it was a semester project where the emphasis was on the DSL itself. So I did not do all that much on the actual search side. At the end of the day, I would probably summarize or describe it as a glorified breadth-first search, what I did, where I applied all kinds of tricks such that it runs a bit faster and uses a bit less memory. And correspondingly, that also only got like 6%, but which happened to be enough to win the Arcathon, since there was not all that much or all that many teams, and also people did not just reuse Kaggle notebooks from 2 years before. Yeah, and that's also when I kind of thought or asked myself, okay, how much further could the score be pushed by just trying to scramble together what's already out there, namely the Kaggle notebooks from the initial competition, which I then did, which raised the score from like 28 to 30%. But that I also just put aside because it's not super interesting, right? I want to work on something that I believe is more promising, and that's also my own code. So, and ever since then, my main focus was actually on data generation. And that's also kind of how me and Jack and Mohammed got to, better know each other. Yeah, I mean, we met on the Yonex Discord server. In an ideal world, or what I wish to be doing eventually, is kind of write a piece of code that can sample from the distribution of all possible ARC tasks, right? Because arguably that should solve the benchmark to some degree, maybe, let's see. But I think this is extremely hard to do, because how do you make sure that whatever you generate, like you sample a random DSL program and sample random inputs, you're almost guaranteed to get garbage as a result, right? So I actually have not really set out to do that as of yet. What I did instead at first was trying to look at the ARC tasks and think of some kind of, not categorization, but tagging of tasks via concepts. And then for a certain number of concepts like object level transformations or grid level transformations or cellular automata, try to come up with some schemata or generator that could produce tasks belonging to such a class. But obviously that cuts it short by much, because you cannot just classify all the arc tasks into some finite classes, right? And then something that I have then mainly been working on was actually the re-arc dataset, where I said, okay, we know that, well, there's kind of two reasons why arc is hard, right? So the great diversity between tasks, if they were all kind of the same, it should be easy. But also the few-shot nature, we only get a very few demonstration examples. Arguably, if either of those two or both were not the case, it should be easier. So I just figured, okay, how well could we do even just something very simple like learning a task in isolation if we had an unlimited number of examples for a given task. So the idea with this re-arc dataset was really try to make some dataset that would allow people to run some more fundamental experiments, because I really believe that's a bit lacking in terms of arc. A lot of people are trying a lot of things, but there's some very fundamental questions that we haven't really properly addressed, I feel. Like, can we solve a simple version of arc, basically?
And then Mohammed and Jack, you guys have got a very interesting solution which is completely different to that, using a large language model, if I understand. So could you, I mean, maybe Mohammed, can you bring it in?
Yeah. So basically, there are kind of two parts to this. There is prior knowledge that we need to incorporate, and there's also kind of arc skills, like general arc skills. That's another also kind of key thing. Like, okay, L-shaped boxes or just grids in general, transforming them, moving them around, recognizing an object over here and an object over there, and those are the same, or just manipulating and playing with arc. And then there's also the generalization piece, which is, okay, now solve a completely new task. So we employ a bunch of techniques. Jack has been amazing at kind of just trying a bunch of things out, and in terms of training, and there's so many techniques, but the gist of it is we do multitask training, and that kind of we think has its benefits. We train on generated arc tasks. Not as many new riddles as people would think, like, but we do train on, obviously we pre-train on arc tasks, and then at the test time, we obviously fine-tune, and we augment and we do whatever we can to get the model to basically generalize and do this kind of novel finding of transformation and so on. But it's all using neural approach, basically.
Okay, so just to play that back, so you fine-tune on a whole bunch of arc data which you've augmented, and then at test time you do this kind of what we call active inference in quotation marks, which is where you augment around the test instances, you fine-tune the model, and then you do inference on that model, and then that's your prediction. Yeah. Very interesting. And that got you guys up to 34%, which was the winning score on the private set, which is amazing. We didn't cover as well, maybe Jack, you can explain this. How did you, because obviously a language model has a bunch of tokens, right? How did you kind of set up the problem so that a language model would, I mean, did you have to try many different types of representation, or what was it obvious which one was best?
Yeah, that was kind of a long process, actually, of empirical investigation to come up with what is the best way to represent arc to a language model. And I did probably 20 different kind of mini experiments in formatting the data in various ways. And so we started working with language models before they became super popular. This was kind of back in the GPT-3 era, before like everyone knew that it was going to be like such a hot thing. But anyways, I kind of experimented with GPT-3 and even did some fine tunes on GPT-3 with some different ways of encoding the riddle. And so went from that to doing fine tuning with various other models. And so it's presented in a text form to the model, and the data set itself is in a text kind of JSON format, and we reformat it in a way that it can fit within the context. And so that's one thing I think Chollet really did kind of a brilliant job in the construction of it, and even the size of the riddles can be like a really hard challenge of how do you get this into the model so that you can get a good response from it. And so part of my approach to it was to think about the construction of a sentence and to set up the construction of the riddle in as close as possible a parallel construction to what a sentence might be. And so it's kind of like the whole thing is like a paragraph. And so it's trying to minimize the number of characters, but it's also like trying to put it in a form that would be the most familiar to the model and that the model could make the most use of.
Could you speak to that? So this is a self-attention transformer, and it's really good at this kind of permutation invariance. And I guess the thought occurs on the one hand, something like a CNN vision model. Do you think that would be better for this kind of reasoning, or do you think there's something interesting about the language model in particular? And presumably that was the reason why you encoded it in this way, to pick up on the strengths of the language model.
I think that would be a very interesting, like, empirical question to answer. I think that if you look at some of the research on universal transformers, and there's even like a version where they have incorporated elements of RNNs and CNNs into those models, and they do find like some pretty interesting things in terms of like algorithmic learning with that kind of approach. So it may be that using something like a CNN would be something that would be like it might enhance the performance. Now, on the other hand, I would probably want to focus more on just using data to try to get the model to be able to learn as much as it possibly can without putting something like a CNN in front of it. Because when you do that, I think you're going to limit the generalization of the model. Now you might be able to do it in such a way that it could be more multimodal, and where you could, take both text and maybe have like some kind of a cross attention thing. And so I think it would be possible to maybe preserve it and alter the architecture. It's just not really something that we've found necessary to do. And so that's kind of one thing that I try to do too, is see how far you can push the existing kinds of models without tacking something else different into the architecture. And I think that actually has been a pretty fruitful thing in terms of like discovering the weaknesses of the models, but then trying to find ways that actually mitigate them. And I think we found several interesting things.
So this gets to a really interesting point. So you made the comment before that symbolic methods are incredibly deep within a narrow domain, and machine learning models are very shallow within a general domain. And so you're basically saying that because you are augmenting a general model to make it deep in a specific, like in this active inference sense, then you have the benefit of it being able to transfer to lots of different situations. But the thing is, though, the model still has, even that, it might be a multimodal model, it might be trained on lots of different types of data, but it still has the inductive prior, which is this self-attention transformer, which is quite limited. The beauty of writing programs and composing together program templates is you can mix these priors together in a very principled way. So you can have a combination of permutations and translations and sorting and all of these different things mixed together. So there's always the question of, well, what do we do here? Do we only use programs, or do we have a hybrid approach where we have different models with different inductive priors? Or do we do what you do, which is we have one foundation model, but then we kind of fine tune it with different knowledge priors on the top, informed by the test instance? It just feels like there are so many different approaches here.
I overall agree with Francois's sentiment or take that there are those kind of two types or classes of approaches, and arguably maybe we would benefit from trying to combine them in a neat way, right? That could have many different forms. You could say, let's use a deep learning model to try to inform our search or whatnot. Not all of that is obviously completely new or has never been done. So, I'm sorry, what was your specific question again?
The question was the trade-off between, on the one hand, just having pure discrete program search versus having a single monolithic foundation model versus having a hybrid of different models with different inductive priors.
Yeah, I'm not completely opposed to eventually trying to reintroduce some of the symbolic aspects, like try to work with a DSL in some way or another. But as of now, I'm pretty happy with what we're doing, and in some sense, going fully end-to-end is also really beautiful. So, yeah, but maybe Mohammed, you have something better to say here.
I was just gonna say, like, at least to me, this kind of problem of wide search is very difficult to do in many other ways, and we kind of have seen the proven way to do it in some sense is to use SGD plus a model. The problem of finding the object in an arc riddle is not so easy because you need to know about the whole objective. So again, this comes back into play, I think, to me. So I think neural networks are really attractive from the sense. In some sense, you can say that the goal, it's really interesting. There's a way to look at the whole ML field as the goal of the whole ML field as having the goal of one algorithm, optimizer plus neural network that's able to learn, I wouldn't say anything, but as many things as we can, right? So that's one way to look at the whole field. You could look at it as making many different, very skilled and narrow neural networks. But if you take a step back, you could kind of see, okay, but they're all trying to figure out one algorithm, and applying that. I think there's been a lot of progress in terms of if you agree with kind of that these are perceptual problems, then you kind of have to see that there's a very flexible search going on. It's very, very difficult to do flexible search over priors with kind of programming. Compositionality is extremely important, right? And it's something we think about and we try to incorporate in our models. But we try to incorporate it within the neural network. There are some interesting specifics, like you could also kind of, like Jack said, just look at what improves these models and look at this as a way to improve machine learning rather than finding a new algorithm. And we do have a paper that's gonna come out that goes into these specifics and kind of how to go deeper, as Jack puts it. And there are some really interesting things there that I think we could really dive into maybe when the paper comes out.
Yeah, what's the name of the paper, or is it is it Secret Squirrels at the moment?
Name of the paper, we don't have a name yet.
You haven't got a name yet, okay.
We haven't published it yet, right? So, but it is in the works.
Could we just come back to this? Because you said earlier that you don't really see a distinction between type 1 and type 2, and like the concept on top of, she's on top of the world, or I'm inside the television, or this blob is inside the container. It feels to me like we have this perceptual processing, and that allows us to transform a problem into this abstract representation. And then the magic happens, then we do this compositionality. And for me, that's really fundamental. And when you look at the state-of-the-art vision models, they're incredibly good at perception, but the worlds that they generate don't make sense. Things are in the wrong place because they're not respecting these axioms about how the world works. And you could argue that there are universal rules about how the world works. And to me, like when mathematicians do deduction, a lot of people just think that all mathematics is deduction when you do conjecturing, because we have all of these base axioms and we just kind of mix them together and we create this path creatively, and then that's the result of the conjecture. But this magic thing happened that we figured out how to trace this path through this space. So anyway, like that's a bit of a rambling way of saying, like, to me, there is something very important about this kind of compositional type 2 space.
You raised a very good point. I'll just, I hope I'm not talking too much, but you did raise a very good point about both of them. I guess the point where we disagree, or where we could dive in even deeper, is what's more important in this case. The point I was trying to make, like you said, there is this perception involved, and then there are two types of kind of thinking, right? There is logical inference, adding this and this mathematical equation, mathematical proof, going through it, and obviously you place a very high importance on that. But there's also dealing with things to frame things into a perceptual problem. Like I need to first see the apple, and then see that I have 5 apples, and then I abstract all of the infinity of perception into 5 objects, and then I can do math on the apples and give 3 to Michael or whatever, right? So you need this perception first. Now, the real question is, what's more important for ARC? What's more important? Is it the perception, or is it the type 2 system? And this is where and also, can you do type 2 things with perceptual-like systems, right? That was the point I think you raised at the beginning, where you asked the distinction between system 1 and system 2. Like, does perception involve disambiguating? Does perception involve putting importance on a certain transformation and reasoning about which transformation is more important? Why? Because of the current objective. Is that and how important is that in solving ARC? Right. That's the question.
First of all, I mean, if you look at language constructions, for example, I mean, language is also an infinite space, but colloquial language is very structured, and language models do a very good job of learning the manifold of language. Because, like what we're, putting the pin in the middle of the dartboard, what we're talking about is meta-learning the patterns of composition in this kind of type 2 space, right? So we have the knowledge priors. If you think about it, if it were possible for us to just search the space of all possible Python programs, and we had some kind of constraint on minimum description length, and we had some kind of evaluation function, we would be able to solve ARC really well. But we can't do that because the space is really large. So we abstract it, and we do library learning, and then we do like meta search heuristics. And there's actually a lot of perceptual interpolative structure in how those programs get composed together. So we kind of, I think that's what we do. But the other thing I wanted to point out is, yes, deep learning models, that they do apparently do colloquial reasoning, but it's not inventive reasoning. It's kind of memorized or crystallized reasoning. And I think that was the point that Jack was saying at the beginning. But the remarkable thing is, even though language models are finite in their capacity, they still have enough capacity to capture a hell of a lot of colloquial reasoning sort of compositions. Jack, you're nodding your head. Go for it.
Yeah, I think think you raised some good points there. And I think a point you made earlier about, like, if you see how these models kind of end up with a lot of distortions, and I think, like, also though, you see like this pattern over time of the models like getting better and better with respect to those things. And so there's something to me that I would call like cognitive resolution, meaning that there is like a way where cognition can be more granular, or it can be more fine-grained. And so the smaller the model or the less training it has, the more granular it is, and the fewer the number of like concepts that can come into play as a part of like the generation process. But the more training that you have with a model, and the more data that you have to train the model on, you get this higher and higher level of cognitive resolution. And you can even see it in kind of a literal sense with some of these vision language models, that if you kind of explore what the model is able to perceive in an image, that the better the model gets, the more it's able to perceive like fine-grained kinds of features. And to my mind, like, that's going to continue over time, where these models have more and more fine-grained kind of resolution. So if you take that back to maybe thinking about like mapping all these patterns over like the colloquial spaces and things like that, that like, even though these models might have primarily crystallized intelligence, you can go a long, long way with that, it seems like. And we don't know kind of what the limits of that really is. And so if you like think about that 10 years from now, and they learn more and more about what kinds of data to train these models with, and that resolution gets higher and higher in a cognitive sense, that I think you get some really interesting things. And it's sort of, so you could reduce these models to like thinking about it from a mathematical sense, that it's just mapping a continuous distribution, and therefore it can't deal with any like discrete kinds of reasoning. But I think there's a lot of examples that even language models themselves are, I mean, the task is a discrete task, and language, in a sense, is discrete.
Two things. First of all, yes, so the language models, they have a high level of cognitive resolution, and this is part of the reason why they overfit, and they learn these weird alien surface statistics which surprisingly generalize very well for natural data. So, for example, they can just look at the texture or the fur of an animal, and they know that it's a cat. And I agree with you that it's not only surprising how far it's come, it's presumably going to go a lot further. But that means these models are working in a very alien world of cognition, which is nothing like the way that we do cognition. And I don't think it's necessarily the case that they can't do discrete interpolation, because language models are a continuous representation of a discrete space. I think what Chollet set out with the ARC challenge was simply a knowledge gap. It was designed to show if the model doesn't know about something, then it won't work. And in the natural world, because there are these continuous interpolative manifolds, they kind of do know almost everything, because almost anything you could say colloquially that could be understood by something else is on the manifold it's already learned. Therefore, apparently it generalizes. But ARC is the existence case of something which was not in the data set that it was trained on because it's something completely new. Therefore, it doesn't have anything to say about it.
Yeah, I think like it is great for that, really. And even like if you take a language model without anything extra and you run it on Arc, they don't do that well. And like when we started working on this, we went at least 6 months without getting a single point on the hidden test set. And after lots of fine-tuning and work and nothing, then finally we got 1 point, and that was, that felt really good after all of that time. But it wasn't until like we started using some additional techniques that we were able to get the gains. And some of the gains are like over 1,000% over what the model really can do itself. And
I mean, could you guys comment, though, on, we spoke about whether this is a violation in principle of the measure of intelligence. So the measure of intelligence basically says that the amount which you go outside of the bounds of your knowledge and experience, that generalization margin, the efficiency of the expansion of that margin in respect of how much experience you have, that is your intelligence. And what you guys are doing, in my view, is you're kind of like, you're adding in a lot of extra experience, which means the conversion ratio is lower. So would that mean a common sense interpretation is your system isn't demonstrating the intelligence? Or could you argue that because you're doing this active inference and you're doing it in the neighborhood of the test examples, then the expansion is still significantly more efficient than it would have been if you trained a base model from scratch?
I don't see a lot of difference between like doing this with an LLM versus like doing that with like a DSL, or where you have to actually engineer the solution to the problem. And like you could completely frame it in a different way and say that the amount of human design that goes into making a DSL is cheating on Arc because you had to design the system's behavior in a sense. And it's also like our system, what we've tried to do and have actually literally done is to induce within the model the functions of the DSL. And so if you take a DSL and you think about like its kind of search space, and then you use that in order to generate data, and then you take that space and you induce that into the model, I don't really see like how that would be something that would be like cheating, if that makes sense, in terms of the spirit of it.
Yeah, no, first of all, I agree with you in principle that I didn't mean to imply that there's a difference in kind between, purely symbolic and deep learning. So, for example, if you did a brute force search of all of the possible Python programs, that would not be intelligent for exactly the same reason. Because what you've done is you've generated loads of experience and your conversion ratio is very poor. I think in your case, what you've done is you've started with something which is already very inefficient because it's a language model. And then you've generated lots of DSL augmented experience.
One thing to remember is you cannot really learn without having some kind of prior knowledge, like we spoke about, right? Like you cannot learn from scratch. So you do need the prior knowledge embedded in somewhere, somehow. And it is really important, right? So yeah, basically, you do need priors to learn, and it's I mean, it depends on how you define generalization. It seems like the ARC dataset has defined generalization as exactly this, learning a new transformation that you have not seen before. And so if that has been achieved in some sense, that is by definition generalization. It's kind of difficult to see the cheating argument, to be honest. But I will kind of go back to the reasoning piece, where we do think you do need the prior knowledge, but there is that little bit of the cognitive resolution argument, right? And within the cognitive resolution, there is flexibility. There has to be flexibility for you to classify in distribution images. There has to be some kind of flexibility, and that we think, like, that is the kind of the core of our idea. We think that little piece of flexibility is actually very meaningful. It is composable. There's a way to get it to be deeper, and there's a way to apply that on ARC. And it's and you do need ARC training to get there. Like completely unseen ARC riddle, you don't even know where the board starts or ends. You don't know what the objects are. You don't know what type of there's also human distribution. You don't know what type of human riddles you could come across, what board sizes you can expect, the range of them at least. There's all sorts of things, maybe even slightly similar riddles. Although I think given what I know about the number of concepts that we've trained on, right, versus the number of possible concepts in ARC, I also doubt the memorization or cheating argument would hold.
Maybe if it'd be okay, Tim, if Michael could talk a little bit about kind of an experiment that we did that was based on a smaller amount of data, like specifically on the ReArc data.
Jack has been training a model on this ReArc dataset, which, I mean, to maybe make it clear what I did there is I took the 400 training tasks, and for each of those wrote a generator which can produce new examples from that task. And in doing that, I made the task slightly more general. Sometimes the background color is fixed, but it need not be fixed for you to be able to apply the same transformation function to figure out the result. So basically, that was a dataset of 10,000 examples for each of those 400 tasks, where Jack has been training a model on that. And this has gotten quite nice results. Actually, Jack, you can probably better describe that in detail.
Yeah, when you run the model like zero shot on the hidden test set on ARC, it doesn't do well. Like, maybe 1% or something like that. But when you run it through our whole system on the hidden test set, it can score up to 23%, which is, basically a state-of-the-art solution. When you look at like the previous symbolic approaches, where 21% was the highest that a single DSL system did, when we trained this model on a much smaller amount of data, a data that was limited to the set of concepts that are in the training data set of ARC, that it achieved basically a state-of-the-art performance with that when you combine it with the rest of our system. So I think that kind of shows, or maybe is like another argument that, that these models are not just memorizing an entire domain, that there is maybe something special going on here.
I guess what you should, either you say they do more than just memorization, or you say, okay, 22% of the hidden tested is a duplication of the public training set, right? Or something in between.
So there's the measure of intelligence, which says basically the generalization must be kind of normalized by priors and experience. So it's a case of, do you count the foundation model training as being that experience? I think you absolutely should. And then just to bring in what Jack and Michael, you were saying. So first of all, you've transformed the model to kind of augment the manifold of language, which means you're using the generalization power of the foundation model in your system. And then you're doing this re-arc, so you're doing the augmentation of arc. Because the other thing with these language models in general is they're not very good with low frequency data. So if you expand the data set with augmentation, and then you basically put a whole distribution in, which is augmented around the language distribution, then these models are actually starting to stretch and generalize on this new problem. So you've designed this brilliant way to make language models generalize on arc problems encoded and augmented in this particular way. But I would still say that in principle, this is still a model that has been trained on, God knows how much data. Could you make the argument that it's intelligent?
I'm kind of agnostic to using that word anyway. Or maybe one small correction first. So you're talking about augmentation, but with rearc I don't do any augmentation. I generate new examples from scratch. So kind of the generator specifies the distribution. They're kind of reverse engineered. But either way, I would say this is actually kind of something I disagree with a bit here. In the sense, if you ask about, like, at the end of the day, fundamentally, we're interested in the behavior of some system and not necessarily in how it's implemented or how it would look like if you would try to open it up and look inside. So at the end of the day, that's also the only thing you can really measure, right? So at the end of the day, you have some system, it has some certain performance, and then whether or not, or like how you interpret that, or whether or not you call it intelligence is kind of irrelevant. At the end of the day, you care about how something behaves and not how it got there.
I'm not a huge fan of behaviorism. I think how we do the thinking and how we do the cognition is very important. I mean, for me, the spirit of this measure of intelligence is we think, and maybe we're wrong, but we think that humans have a bunch of base knowledge and we efficiently do reasoning. And language models have been given this vast amount of data. Now, I get that you could say, well, actually, we have a vast amount of experience, and maybe we're doing something that's not too dissimilar. You could make that argument, but it feels like you could think of our cognition as, in the moment, we are constructing skill programs very efficiently, and we're coming up with an answer.
Just one quick thing. Also, I would say, or at least I personally care more about getting something to work and less about trying to reverse engineer how we do it. Or at least I very much expect any kind of more advanced AI systems to be just very different from how we are.
Well, I kind of agree and I don't, but let's do the agreement bit first. So I think the reason Chollet came up with this was on Kaggle, around 2017 or whatever, he noticed that all of the solutions didn't generalize beyond the instance of the problem, so they couldn't be applied to other types of the same problem. Now, that is not the case for what you guys have done. So you could, in principle, find another similar type of problem, another archetype challenge, and you could do exactly the same thing because you would, do this dataset generalization and do this like active inference and fine tuning, and it would work. So you could say, oh, this is just a no true Scotsman argument, right? Your thing works and I could do it again in another domain. Therefore, what's the problem? And so maybe it's just a philosophical argument that I'm saying, well, that's not really intelligence. I don't know.
I mean, it is really interesting. I mean, ARC is a behavioral test, right? So it is a behavioral way to try to tease that problem. Your point is it might not be a very good behavioral test if LLMs solve it or they don't and so on. But I do agree with you in that, okay, it's unsatisfying. We have to dig deeper, right? I think that's what you're saying. First of all, we have to say, okay, what do we define as generalization? Do you define a completely novel, difficult arc problem being solved no matter what happened before, is that generalization enough to you or not? And then, okay, I think that's also an important question for us to ask ourselves, just so that we're able to talk. But then also, it's not super, it may not be super satisfying, and we want to dig deeper. Okay, what made the LLM solve this specific thing exactly? What's the important thing? I think that's a super interesting question that a lot of people want to answer, and like I'm super excited to work on that, to kind of figure out why our neural network solved it and what exactly it did, and how it got to that solution, trying to provide more than behaviorist responses, because I think that's also super useful. And perhaps it would answer the question one way or another. I agree with you that it is unsatisfying, basically, but at the end of the day, performance and behavior is also super useful. That's why these things, LLMs, are useful in their specific domain and their specific narrative, and they do useful things. So behavioral thinking is useful, but I agree that it is unsatisfying, and I hope that we can figure out why, and I would like to work on that even.
It is interesting in the sense that if your data set, I'm not using augmentation, generation, if it was just based on some fairly first principles based transformations and extensions of the existing example, so something that could easily be applied to something else, I don't have a problem with coming up with new priors for another domain on a different type of problem. It's all about the meta learning and the reasoning. But we have been thinking of that as a search process. But in this particular case, you're saying, well, when we leverage the language model, so we fine-tune the language model on all of this generated data, and now when we sample from the language model is doing the meta-learning and the reasoning. That's interesting because, the whole hypothesis that I've been going on is that doesn't happen in a language model. A language model is a retrieval system. It's not doing this kind of patterned meta-learning. But you're saying that you think that can happen if you can transform this problem domain into the existing manifold of the language model.
Yeah, 100%. There's very clear parallels of associative learning that you could see as happening. Now there's no proof of it, but there's the tokens themselves and the way self-attention works dynamically in the forward pass. There's a dynamic model being built up in the forward pass, and in just the forward pass, there's a dynamic model that you could kind of see associations happening within it, or you can see how that may come to be. Now, whether that's actually happening or not is a very interesting research question. And that is kind of our prior. That is how kind of me and Jack came together on this. We kind of saw this as kind of the same problem, and we were like, okay, and these are really good at that, and we can probably get them to be better. So but yeah, no, I think we do have to dig deeper.
Yeah, I mean, to me, this comes down to the notion of creativity in general. So, and it's also related to an analogy making. So, part of creativity is about being able to map seemingly disparate things to things we already know. And it's also related to this idea of core knowledge, because you could argue that everything we need to know is represented, let's say, in our language or in these existing models, and there exists a mapping function which we could trivially create for something off the manifold to transform that problem into a problem we already have, and then we can just use the existing language model. But to me, I've always felt that there are so many examples where we do need, ingenious creativity in the moment.
I think that is the case, and we're not saying that transformers can do everything. We're not saying that LLMs are far from it, but we do think there is a little bit more, just a tiny bit more, than the skeptics would have you think, and we're operating on that. Now, whether they can do true creativity, I think there's something interesting to be said about learning and arc and perhaps even creativity. I think you do need some kind of learning to be able to form new concepts, because like you have this pre-existing map, your pre-existing frame of looking at things, and the only way to kind of change that frame is you need to adapt, right? And so there are many issues that prevent language models from doing that too much. We think they do them a little bit in the attention maps, but they have, for example, a frozen tokenizer, right? They cannot come up with new tokens. And it's not just a question of coming up with new tokens. Even if you could easily like go into the neural network and add another neuron, and there's your new token, but has not abstracted over its inputs in a good way, such that this new token means something well. And the way to do that is with feedback and with, an optimizer and so on and so forth. And that's how you get a new abstraction, a new class. And you do need learning for abstraction.
Yeah, that's really interesting. And I completely agree in principle that there's kind of agential feedback system, so you can kind of like lean in to the specific instance of the problem is very important. But just to kind of like slowly wrap up. So first of all, how much generation do you do at inference time? That's the first part of the question. The second part of the question is, you've got up to 34% now. How far do you think it can go? And there are people like Dilip George who have said that it's because of perceptual leakage, or, there might be some upper bound on how far you can go with this model. So, I mean, how far do you think it could go?
Well, it's kind of a bit of an open question in a way. And so we do have like some projections that we think might be possible. And I wouldn't be surprised if without a lot of innovation that it could eventually go to 50% or higher. And I think with additional innovations that, well, I don't know if it could get to 85% or not, but I think it can definitely get like somewhere over 50%. And so about the perceptual leakage kind of detail, like ultimately when it comes down to it, nobody has seen the answers. So regardless of whatever kind of approach you're taking, either a symbolic approach or with a machine learning approach, you don't have access to the answers of the hidden test set. So there has to be some degree of generalization that occurs. And in terms of like how much data we use, like relative to the amount of training data we use, that's like a tiny amount. And so one thing we kind of see too, there seems to be like a scaling law in terms of how good a model has become in terms of like how much data it needs in order to be able to fit to a test time distribution. And the better the model is, the less data it needs at test time in order to be able to solve the problems. And so I would say, there probably is some degree of that perceptual leakage. But at the same time, I don't think it's all that way, just, based on looking at the items. And so there are like a number of items that are, I would say, more idiosyncratic rather than patterned, following like a clear kind of a pattern. And I think Chollet has said himself that like eventually he would like to have them essentially all be kind of idiosyncratic, where like you kind of couldn't predict the content of another one based on the content of one of the items. And So yeah, I think there's probably a little bit of that leakage, and even to the extent that, like, you can look at some of the existing symbolic solutions that are like really crafted for like a very particular kind of a problem, like repairing a mosaic or something like that. And so there is obviously a little, at least some degree of that kind of leakage, but I don't think it's 34%. I think it's
Interesting.
yeah.
Interesting. Another thing I was thinking about is so the ARC challenge is actually quite restricted in a sense. So it's been the problems have been designed with these core knowledge priors, so objectness, goal directedness, numbers and counting, and basic geometry and topologies. I mean, maybe Michael, you'd be a great person to answer this because you've done this dataset generation thing. But roughly speaking, you can whittle it down to. I'm not sure how many transformations you had, Michael, but let's say on the order of 30, or maybe 50 or something. I'm not sure. And so that's not task specific; it's domain specific. So this is an interesting thing, right? So now when we use ChatGPT, it's not domain specific at all. I mean, I can ask it about almost anything. And when we create this active inference thing that does this, domain specific data generation, it's now a specialized model, isn't it? So how do you think about that? Do you think it, in the future we might have lots of specialized models for doing certain types of things?
I hope not. I hope it will just be one 50-line Python notebook or something that does it all. But yeah, maybe a little bit of input there. So basically, the data generation and the model, they are not directly tied to each other. There's some more than one ways in which I do generate ARC-like synthetic data. And then on the other hand, there's the model. In terms of the concepts in the DSL, I view it as it's just a toolbox. Not everything is a transformation of an object or a grid. There's also helper functions. There's also stuff like detecting a property of an object or a grid. And most likely it's a Turing-complete language, so it's very flexible. There's 160 primitives, but I know I can reduce it down to like 30 if I try to, or start rewriting the DSL within itself.
What I was getting at is for ARC, there's about 100, I think you say 150. But if we wanted it to work on any problem, wouldn't that blow up? And then we've got this exponential generation problem.
Yeah. Well, I guess the question is kind of meaningless because, as I said, I can try to rewrite the DSL to use as few functions as possible, but with the same semantic expressivity. So I would have suddenly less concepts, but the same expressivity of the language. And I can obviously also do the reverse. I can, for each composition or combination of coupled primitives, add it as a new primitive. So I'm not quite sure. Like this question of number of concepts or primitives, like is a combination of two concepts a new concept? I guess depends, or up to the person to define.
Okay, but in principle though, we're generating a data set to fine tune a language model. Mm-hmm. And that data set grows exponentially with the number of combinations of these primitives. And, we're not talking about infinities here as we've described. It's highly structured and it's more parsimonious than we, might have thought, but it's still huge. And that to me suggests that just, especially if we're doing test time fine tuning with active inference, I mean, just to give an example, there was that Tree of Thoughts paper. And OpenAI were talking about Q star, weren't they? They were talking about doing some kind of test time, trajectory optimization. And the reason we never saw that, presumably, is it's too slow and they couldn't scale it. They couldn't make it work. So we're going to have this problem that in principle, we could do all of this clever stuff, but the data set's too big and it's just too much test time inference. So for ARC, because there are, relatively few knowledge-informed priors, we can do that in tractable time, right? But if we start broadening that out to a very general model, it would become intractable for us to do that at inference time.
I would definitely agree with the last point, but I would also say that even within the arc domain, I mean, the number of possible problems that you could generate or come up with, it's extremely big already. So
Now, I don't know for certain about that. Like, to some extent, I can see your point, but like, I think one reason that we need so many training examples is that the base models don't have already a great number of priors that they can draw on. So if you imagine that we could apply some of the process to like a very large model, like a GPT-4 level model that already has within it a great number of priors, the amount of data that you need at test time grows much smaller. And so we even see that with models that are trained to a different extent. There's a great variation in how much data they need at test time in order to give their best performance. But there's also a scale on the model size. So if you go to a larger model, you need a lot less data in order to be able to get the same performance out of the model. So if you keep scaling that up and you have a model like, let's say, GPT-4 Vision that has a lot of visual concepts within it, that it wouldn't take nearly as much data in order to learn and perform well on ARC, because it would pull in some of those concepts that it's already learned, if that makes sense. So I don't know that like the amount of data would explode at test time.
Arc is quite contrived in the sense that it's just like, one shot. But in the real agential world, I think what you said makes a lot of sense, because the first time I generalize to a new class of problem, I might have to do lots of simulate. I mean, this is what we do as humans. We do lots of simulations of the world, and we kind of think about what things might be in the future. And then it gets kind of baked in. And the next time I see that situation, I'm not dealing with novelty anymore. So it's not like every single time we'd have to generate loads of data. The actual agent that we build would be durable. It would have a memory, and it would remember all the stuff that we did before. So that's another argument why it might not be that big of a deal. And your point is well taken, that if the model is bigger and it already has more knowledge, then you don't need as much generation to fill in the gaps.
No, I agree. I was just gonna say it doesn't have to be exponential with respect to the concepts, as in you're going e to the n, where n is the number of concepts. It could be, I think Jack's point basically was that it's actually o to the n, probably. If you have priors already, right, you could reuse them. Like from GPT-4 Vision, you could possibly you'd have lesser training time, right? It doesn't have to be o to the en. It could be o to the n. It depends on how you see compositionality within the model kind of working out, basically. Yeah.
Guys, this has been amazing. What do you want to tell everyone before we go?
Have a look at the ARC tasks. It's a whole lot of fun, very addictive, and hopefully you can produce something useful or insightful in the process of dabbling around with it.
Yeah. Play around with ARC. It's very interesting. Try out all the approaches, see why it fails, and enjoy.
I have to say that ARC is super fun and addictive, and so be warned ahead of time that if you like hard problems and you go down this rabbit hole, well, it might be hard to escape. So be warned, and I think Chollet has kind of done a brilliant job with this, and like so many people have amazing creative ideas that when they kind of apply even like their own personal knowledge to some of these things, it just kind of blows my mind sometimes what people are able to come up with. And so I'm interested to see what all the creative minds out there are going to do too. Well,
anyway, guys, this has been amazing. Thank you so much, and honestly, great work on your respective submissions for the ARC challenge. It is a beautiful challenge, and there may well always be people like me and Gary Marcus who will move the goalposts, after you've solved it and claim it's not really intelligence. But I think you'll accept I did grant that what you've done is very interesting, because it could solve Chollet's original concern, which is that it could be applied to a new type of the problem, and I think that is a difference in kind. So my congratulations to you.
Yeah, thank you very much,
Thank you so
and
much.
thank you for inviting us to do this. And like, to your point, I think we need skepticism, and that helps reveal blind spots that we might have. And
Yeah.
so I think it's all good, and it's thanks a lot, and very nice to meet you.